All right, good afternoon, good morning, or good day to everyone that has joined us here. On behalf of Glencore Technology, I'd like to welcome you to our masterclass on smelter blending. Today, we're going to be going through both an example of how we do blending within both Glencore Technology and the Glencore Group, as well as have a panel discussion about various different ways that blending is done on our sites. And then also we're going to go through a Q&A of the questions that are submitted during the webinar itself. So we're going to do this in two distinct parts. So for this first part, I myself, so my name is Stanko Nikolic, and I look after the pyrometallurgy and hydrometallurgy groups here at GT. So I'm going to be taking you through the worked example and how we do blending. And then at the conclusion of this, I will be handing over to two of our pyrometallurgy specialists who will be waiting to in one of the other rooms that we have to be able to go through the panel discussion and Q&A. Now, with the Q&A, how are we going to do this? So what's going to happen is that what we'd like you to do is to submit your questions as we're going through the webinar itself. And essentially, it's going to be, in a sense, a first question asked will be probably the first one that we answered once we come to the panel discussion and the Q&A section. So please shoot in your questions. We're not going to be actually answering them until we get to the panel discussion session. So if you shoot through that question, hold on to it. We will get to it once we get to that panel discussion and Q&A part of this webinar. Now, rest assured, if there is a lot of questions that come through, we will work our way through them, and we will then issue you a response if we don't get to it during this actual webinar and discussion itself. So the other thing to note is that the webinar will be recorded. So don't worry if you missed something. If you want to have a look at how we did something, or if there's a key question that you want to hear answered again, then that's something that you will be able to access after the fact and be able to really get in there and see that detail and understand what it is that you need to understand for these next steps. All right, so let's move into the webinar itself. Let's hope. There we go. So what today's session is all about is our smelter feed blending masterclass. So really what we are looking to do with this webinar series within the pyrometallurgy area is go through a range of masterclasses of how we do things within the Glencore Technology team to be able to look at how we optimize or improve the performance of various aspects of the smelters which we deal with. Now, when we talk about smelting here at Glencore Technology, we are mainly focused on the base metals area. And so that is the copper, the nickel, the lead, the zinc, and the tin. So that's probably going to be a bigger focus of this masterclass series. When we look at today's session, it is going to be heavily focused on the copper side of the business. But everything that we are going to be presenting and talking through today is applicable to all furnaces, be it ferrous or non-ferrous, or in base metals, or in a precious metals plant that is using the base metals as a carrier. So it's regardless of what is your approach. That's an area that we have ISASMELTs running in, is all those different areas of the base metals and the precious metals. So it's something that we have great experience in and want to take you through our understanding of this space. But really, when it comes to what is it that we're going to be looking at today within this particular session, I thought the best way to kick this off is to look at what is it that we're trying to achieve with the feed itself, or what are we trying to achieve in a smelter itself. So it seems my video is refusing to load. So let's try that one more time. There we go. Hopefully you'll be able to see a video up on your screen, which is looking at the feed falling into the ISASMELT furnace in one of our operations around the world. So when we think about feed blending within a smelter, really what it is about is making sure that what we put in the front end, so as you can see here, simple feed preparation that's been done. It's just a mixed concentrate that's still got some inherent moisture within it. It's mixed in with the fluxes and fuels and just dropped in through the roof port in the top of the furnace. We want to make sure that what's dropped in through that into the furnace is then able to be smelted to make the right products that we want in the furnace itself, so that then it can feed the subsequent parts of the smelter flow sheet. So that's really what we're talking about today, is being able to understand how do we do the blending. Now, this is more than just preparing a single smelting blend. This can also be looking at the longer term trends of, hey, I want to look at treating a different material. I want to look at making additional money for my smelter. How do I actually go about doing that? How do I blend in this feed that I have that's high value? So what we're showing today is a tool that we use to do that, is exactly what you can then use to look at doing that for your operation as well. So it's an ability to, one, look at the operation of the furnace, but also look at the operation of the longer term trends of where do you want to run the furnace, where do you want to be. So you can see here on this image, the simple, our final feed device, putting the concentrate through down into the roof port of the furnace. Just for everyone's interest, what is this thing moving back and forth here in the top of the image? That's actually the ISASMELT lance that's providing the air and oxygen to be able to agitate the bath of the furnace itself and to be able to drive the smelting reactions through the turbulence of the bath. So smelter feed blending, what is it that we're really talking about here? And when we consider what's one of the most important things for all smelters, regardless of technology, we've used that ISASMELT example, but within the Glencore group, we have flash furnace at Passar, we've got Noranda reactors at the Horn smelter in Alto Norte, we've got other ISASMELTs and operations in Kazzinc as well. So we have a range of furnace technologies within the Glencore group. When we look at all of them, what is one of the key aspects of being able to be important for making sure that our smelter runs well? Really, we look at it, and homogenization of the feed inputs is one of those key factors to be able to maximize stability within the smelter itself. So really, when we consider what this is we have to know the composition. So then that's us having the right composition that we're feeding in to the furnace. We have to have a steady composition and have this sort of measured and controlled rate. Now, when it comes to all the different furnace technologies, when we look at the flash smelters within our group, they have much tighter bands with what would be considered the right type of composition for being able to operate the furnace. When we look at the ISASMELTs and the Noranda reactors, that's one because it's a bath smelting process that has either a big buffer of molten material like the Noranda, or the large turbulence of the reactor in the ISASMELT, where you're able to have a much broader composition of materials that you put in the furnace. And so what's considered a right composition is actually much broader for the ISASMELT and Noranda when compared to others. Now, also when we consider what are the other factors that are about how do we get this feed preparation and blending correct, it's about this right composition and making a steady composition. So that's really all about making sure, how do we actually go about ensuring that once we know what we have on the different areas of our smelter, or what's coming in on the ships to the plant itself, how do we actually make sure that we are then able to create a blend through the feed system that we have that will be able to be treated and be able to be smelted by our actual operation. And when we look at feed preparation, One thing that's really key there is to do with the homogenization. Now that can be done through mixing of the concentrates, that can be done through proportional blending. Also then when we consider what's important in homogenization, moisture is a really key factor. We have to understand and be able to make sure we have a uniform distribution of moisture. If you have large amounts of moisture, regardless of smelting technology, that can result in sort of a fluctuation in the pressure in the furnace, and that's something that will have to be handled by the gas handling system. So that's where the advantage is of the stationary closed seal furnace technology like the ISASMELT is, where you're able to then deal with these pulses within the system and minimize emissions to the environment. When we look at then what's required to be able to get the feed to the furnace, it's really important that we have this in a measured and controlled rate. So really what we're talking about there is the feed system has to be designed so that we eliminate surging, that we are able to have a smooth, consistent feed to our furnace plant. So really, when we look at what we're trying to do here within the smelter and what we'll be going through today is being able to go through what you see in this image on the right-hand side, the concentrate that's coming into the sites, to be able to make sure we can pass that through the smelter to be able to make our copper anodes or our final metal product for the other base metal types at the end of our smelting route. So that's really what is key here for what we're going to be going through today. So when it comes to what is it that we're going to be, or how is it that Glencore Technology do the blending, I'm going to be taking you through an Excel-based tool today, which is one that we've developed here at Glencore Technology, which has been rolled out to a number of the sites that we have. So this has been rolled out to both the ISASMELTs as well as we've been rolling it out to our flash furnace site as well. So this is a tool which is based in Excel, Microsoft Excel, as you see it in front of you now. But it is a tool that then has plugins which are built into it to allow you to be able to then understand the impact of your blending on the actual furnace itself. So what I'll do is I'll switch these off and we'll look at a particular case just to start with. When you consider, let's say you are a captive smelter that is treating the same mine feed day in, day out throughout your operation. You've been doing that for 15 years. You can still use this blending model that we have. It could be that you treat various concentrates that you're going to proportion together, that you put in different bins, that you look at putting in together to be then sending to the furnace itself. And so normally for a captive smelter, you won't see much variability in the concentrate that you have. As you can see here, these assays are all about the same. And so therefore, you're really looking at, well, once we have a consistent feed and then you look at proportioning that. So this is a 30, 40, 30 blend to reach that 100%. You end up with a combined concentrate composition. Now, when you're in this case, normally many smelters then they may do some of this process modeling at the beginning of their operation, or they may get the technology provider like ourselves at Glencore Technology to assist them in establishing parameters to run their furnace to, and then you just stick to those parameters, and the furnace operation will be able to run within the parameter, within where we want it, and you shouldn't see many problems. So that is the case for many facilities around the world. But what we're seeing now, and especially within our Glencore Group smelters, is that when you look at where is the profit to be made for a copper smelter, it sometimes is not where the copper is. When you look at concentrate terms or trading from the different companies that are out there to be able to purchase the concentrates, when you look at where that you may be able to get a better amount of profit for the smelter, if you treat a clean, nice, clean copper concentrate, that's not really where the money is going to be for a copper smelter. Where the money is if you're treating a concentrate that is high PGMs, or if you're treating a concentrate that has within it a lot of lead, zinc or arsenic or other actual elements that make it a little bit more difficult to treat within a standard copper smelter. So when we look at the majority of copper smelters in the world, there's obviously a big dominance of the flash technology and others like that. And then you look at those smelters, and they do find it difficult to be able to treat high lead, zinc, and arsenic feeds. And that's where really the ISASMELT come into a niche, into its own, in being able to assist clients to be able to process these concentrates, which might have high lead, zinc, and arsenic, and then being able to push that to the fume, being able to recover that through a dust leaching process, like a modified Albion process technology for dust leaching, which is done in Mount Isa Mines in the Glencore group. And you're then able to actually maximize the value that you get from treating these kind of concentrates. So let's say this may be where you start off with, but as the mine life starts decreasing, you're then going to want to look at maximizing the operating window of your smelter. Now, really what you want to move into is not maximize the throughput going into the smelter. You want to maximize the value. And that's where you start looking at, can I put in some custom cons? And if you start putting in custom cons, let's say at small percentages, and I'll put this one in here first, we can see that then this is a concentrate with a high percentage of arsenic. So that then has lifted the amount of arsenic which is in our feed. So we then want to look at, well, is this something that's possible to be treated? We then look at, well, what could be another possible high value concentrate for a copper smelter to be treating. Another one can be a concentrate that has got high amounts of alumina, high amounts of magnesia, or high amounts of material that is then going to be affecting the slag chemistry of the actual process itself. So then leads you to the question, well, previously I've been running this smelter as a captive smelter. I've known the con, it's been day in, day out, the same concentrate. What am I now going to do to be able to determine, can I put through these other materials? What impact are they going to have on the chemistry of my slag? So many sites look at establishing, oh, I've got to keep within my ranges of operation for the smelter. I can't go above a certain percent magnesia. I can't go above a certain percent alumina. But the problem then can be, well, what if you have both? What if, can you tolerate one that's higher and one that's lower? You have to be able to answer these questions. And that's really where this tool comes into its strength. So when we look at what we input into our Glencore Technology blending model, this first part is purely an Excel formula, which is looking at putting in a composition. You can see here, both of these two custom feeds that we've added are higher in copper. One is higher in copper oxide, and the other is higher in copper sulfides. And we have one that's higher in arsenic and one that's higher in alumina and MgO. Now, all of these come into the feed proportions. And you can see here, this is just an Excel formula, which then looks at making a particular blend. And if we look at, so we've increased the MgO, so we've gone up to 2.2 and 1.5. So if I take these out, again, we'll take a look at the, where we started with there. So we can see that the alumina is at 0.9 and the MgO is at 2%. So what we've done is we've increased, and we have 0% copper oxide in this case as well. So what we've done by adding these concentrates, I'll put these back in, is that we've increased the amount of copper oxide that's entering our system, and we've increased the amount of alumina. For a different site, this could be a question of, is this okay? Can we do this? So how do we do this? How do I actually work out what is the maximum that I can put through in a particular smelter? So when you consider this, really you have to dive into understanding, well, what is the impact on my slag chemistry? That's where this leads to. Now, you can go and look through the phase equilibrium diagrams, pull up binaries, pull up ternaries, go talk to universities as well, which is definitely one option that is open to you, to be able to find out, well, what do the experts believe should be done to be able to treat this kind of material. And that's something that we even do ourselves. We consult with a number of unis when it comes to understanding what is the impact of various elements. We also sponsor a number of different programs which are looking at expanding the research in the slag chemistry space. But that's not something that you can do easily, quickly, and every time you want to look at making a change. And that's where this package or this model that we have has come into play. Now, the particular implementation which I'm taking you through today is one that is using a particular package which we have been co-developing with the CSIRO here in Australia, which is the multi-phase equilibrium package, or shortened to MPE. And now it's a plugin to Excel. Now we put in the inputs here, which determines what is the alumina, what is the magnesia, what is the copper oxide. And what we want to know is, what is the silica to iron ratio that we should be running this process? What is the temperature we should be running? How do we actually answer that question? So to do that, this package does Gibbs free energy minimization of that concentrate. Now, what it's going to be doing is looking at 3 different silica to iron ratios that we have here, and it's going to be looking at it over multiple temperatures. So then it can give us an idea of what is the operability of this slag that we're going to be creating from smelting this material. And then we can look at choosing a particular operating condition to take to the next step of the process. So I'm going to hit calculate here. But whilst we wait for this to calculate, I'm just going to flick back to the presentation to take everyone through the next step of, well, understanding, well, what does this all mean? Because when we think about blending, there's not just one way to do blending. There are multiple ways for a smelter to do blending. And I'm going to take you as an introduction through 2 of those ways. And then both Ben and Oscar, who are going to be coming in after my session, will be able to take you through in a bit more detail those particular methods and their experiences with those methods. So when we look at one of the options that's available to a smelter, it would be what's called the bedding plant, or the bed bedding technique. So this is what is done at our Mount Isa operation. It is also done in a number of different ISASMELT plants, where you're looking at stacking the concentrate with the stacking arm and then creating these beds or layers of concentrate that can then be reclaimed. So this option that you see here is up on the screen. This is one that is a radial blending technique. That's not the only option. You can see here, this is the reclaimer here, reclaiming the front face, or cutting that blend, or that stacked blend of concentrate that we've selected. You can also have inline systems. So we have this at our zinc lead operation. There's also a couple of other ISASMELTs that use this inline stacked blend as well, where a tripicar just moves vertically, creates this layers of the particular blends, and then it's made sure that when it's cut, it then results in a consistent feed to the smelter. So this is one option that's possible. What it does is it means that you have, let's say, a 10,000 ton stockpile feeding the smelter, and it's a known consistent feed for that 10,000 ton. The disadvantage here can be that it's perceived to be not as flexible as the other option, but I'll let Ben and Oscar go through some of those details with you. The other option that is also possible is to look at actually filling multiple bins. So this is what's present on a number of other sites. This is probably more common for custom smelters, where they have a number of different concentrate bins. In this case, in this smelter, there's 6 of them, which can then be filled with different concentrates in the actual bins themselves. So when you look at how blending is actually performed in this case, in the previous case, we loaded the concentrates at different points in time, creating these layers, and therefore cut one smooth composition through the 10,000 ton stockpile. When we look at how blending is done with this bin approach, this is performed by having the actual individual bins have the amount of concentrate in them. So if you look back at the Excel spreadsheet, which I had, then there we had 5 different concentrates. And so therefore we had 5 there that were able to be filled in each of these individual bins. And so then what you would do to achieve the same blend or achieve the same actual final endpoint, it would be that you look at understanding that what you want to do is to set the rate of each of these individual bins to be proportional to the actual same equivalent blend as what you would get with an inline stacked system. So that way you can actually have a bit more freedom potentially in this system where you can quickly you don't have just a 10,000 ton stockpile in front of your smelter that you have to get through before you change the blend. You can change this potentially a bit more quickly. But as you can understand, if you are to change concentrate rate quickly here, then potentially you may actually change your slag chemistry as well. Let's say you have one of your bins, which is one of the concentrates, which has a lower amount of the magnesia alumina. If that one was to decrease in rate or stop, what would then happen is that you would have a high proportion of magnesia alumina in the slag in the furnace. That may impact the slag chemistry, but that would be something that we would look at doing with the MPE package to be able to, and our Excel model, to be able to then look at, well, what is the impact if we make that change, and seeing what would actually happen in the actual smelting furnace path if we were to enact that change. So both systems has the pros and cons, and I'll leave the rest to Ben and to Oscar to take you through a little bit more about their personal experience on sites operating with these 2 different systems. Now, I will now cross back to the Excel model, and it's finished its calculation. So normally this is doing a mass number of calculations, 30 in all, to be able to do these graphs. So it's finished in about 3 minutes or so. That's roughly the amount of time that it would take to do all these Gibbs free energy minimizations for these particular conditions. So what it is has actually presented to us, and we've split this in 2 views for us to be able to look at evaluating what is the impact on the furnace operation. So the first view that we're looking at is viscosity. So why is viscosity important? It's all about understanding, can we move this slag out of the furnace? Can we get it through the tap hole, make sure it's nice and fluid? We've got to keep that viscosity right. When we look at the percent solids, that's something that's very important in an ISASMELT, because in an ISASMELT we can run with solids in bath. It's something that's unique and special to the technology in the fact that the turbulence that we generate with the central injection lands that we have in the furnace, that allows us to keep the suspension of solids. Now, what that means is that we can actually run the furnace with these solids suspended. So therefore, we can actually have a protection layer or maintain the protection layer on our bricks within our furnace. So when you look at other copper smelting technologies, they either have campaign lives of about 1 year or 2 years, if they are just brick furnaces, or they have been extensively lined with copper elements, for example, the Mitsubishi and the Flash technologies. For them to be able to actually have a campaign life at all, they have to have extensive water-cooled copper elements throughout the whole furnace. In an ISASMELT, you don't need any of that. It saves you on all of that capital. It saves you all of that operational difficulty. And you're able to run in just a brick furnace. You can achieve a 4-year campaign life. I think our longest campaign life at the moment is approaching 6 years in one of our copper ISASMELT furnaces, which is at the First Quantum's Kansanshi operation. But when we look at what are we trying to get from these graphs, we're trying to look at an operating point. So really, what do you want as an operating point? You want to minimize fluxing, you want to minimize temperature, you want to be able to make sure you have a fluid slag. So when I look at these charts, I look at the silica to iron ratios. So apologies to those of you out there that are iron to silica people, you'll have to do the maths in your head. But when I look at this, to be able to minimize the silica fluxing, I want as low a silica to iron ratio as I can get away with for a low enough temperature. So when I look at this for that alumina, which is in this sort of 3%, and magnesia, this 4% mark, I'm probably going to be looking at seeing, well, the lowest sort of operating point at a viscosity that I know will work for a copper smelter or for an ISASMELT furnace. Now we can get away with high viscosities and ISASMELTs and other furnaces. We're going to be targeting this silicon iron ratio of 0.8, and we're going to be targeting an operating temperature of, let's say here, 1185. So this low operating temperature would probably be unheard of in other copper smelting technologies. But as I said, we can do this in the ISASMELT because of the fact it's a turbulent vessel. You keep all those solids in suspension. So once we finish this, we can then take advantage of the next power of this package. And this is to be able to do an energy balance of the plant. Now, as you can see, I flicked to this sheet, it's come up with big errors, and you got to wait before you complete this. And why is that? It's because it's going to do an energy balance. Now, to do a proper energy balance, you need to do a speciation. Now, we have a simple tool here, which we've created just to be able to speciate a chemical assay to be able to then perform a full energy balance of the smelting plant. So you can see here, this is then the setup. This is then the input concentrate coming in. I've got here some Lance air. So this is the air and oxygens coming in to mix in the furnace. We've got our silica that's being added as a flux to achieve a particular ratio. And we've got some fuel here. So we can run this calculation. Now here, it's just an energy balance calculation. It's just a single calculation. So this is one that can complete in a shorter time period, and then allows you to be able to look at really defining how is the furnace performing. If I was to smelt this material, now if you remember, we've got this copper oxide that's present. So if you do have copper oxide present in your feed, that then means that, hey, that's going to be an energy sink. I may have to be adding a bit more fuel to be able to treat this particular kind of blend within my smelter itself. So you'll see here, it's completing the calculation. MPE puts its outputs down below here. You can see the simulation's completed successfully. It's now filling in all of the outputs for what it's done as a calculation for us to then be able to go, well, how do I use this? How do I interpret this? How do I look at being able to use this information to be able to work out the right way to be able to operate this furnace? So we can see here, I'll just scroll down, you'll be able to see these are the raw outputs from MPE. You can see gas composition, slag, solid compositions, and matte composition. So it's full Gibbs-free energy calculation that it's done. But what we've done within our tool is allowed that to have the interface within Excel so that we can then see, is everything in the right spot? So you can see here first, we've identified, hey, this is a low energy case. We've got to add more fuel or decrease the amount of reverts for smelting to be able to maintain the temperature that we're targeting, which is this 1185. Now, it could be that we look at, okay, well, this is a low energy blend because of these copper oxides. Well, I'll look at adding a bit more fuel. So this could be solid fuel in an ISASMELT. This could be natural gas or gaseous fuel that we put down the lance itself. Now, we do have another option in the ISASMELT. So that can be that we look at adding in, let's say, a high margin feed. Now, in our case, this could be something that, let's say, let me bring up this composition for everyone. This could be something that has a high level of organics and copper. This could be some type of scrap that we could put in. Now, in the ISASMELT, the nice thing is that we're not bound by having to just add this material in with the feed. We can inject this material also down the lance, which is done on a number of our installations, and then to be able to look at treating it. So we've put in this high margin feed, which has some additional fuel value that it's putting in to the system. And then that can allow us to then complete the energy balance and to be able to look at the impact of that on the operation of the furnace. But I am mindful that I have been talking for an extended period of time, and I do want to make sure that I can see there are a few questions that are coming in, and I want to make sure that I give enough time for the panel discussion to begin. So at this point, I think what I will do is I will cross back to the actual team. So let me go back. So we'll cross back to me to do a summary. But when we think about where we've got to today, I hope I've shown you a bit about how we do our blending, the importance of the slag chemistry, how easily we can bring that into play to be able to determine how we feed our plants. Now, we'll be passing over to Ben Hogg and Oscar Mendoza, who are pyrometallurgy specialists, in a moment to take you through this panel discussion on the smelter feed blending, as well as go through your questions on the Q&A. Now, before we get there, and whilst we do this transition, we will be launching a poll, which will come up on your screen. So I encourage you, please go through that poll, go through the questions, give us some feedback, help us work out how that we make this a bit better. And so that should be coming up on your screens as we speak. So please fill that in. And we'll now be going through the process of passing over to Ben and Oscar, who are in the other studio. So I'll let the IT team take it from here. Please fill out the poll whilst we go through this transition.
Great, thanks, Danko. My name's Ben Hogg. I spent a lot of time working in Mount Isa Mines copper smelter before coming to Glencore Technology. I've seen a wide range of feed blending systems employed within the Glencore group and also outside the Glencore group within our ISASMELT licensees group. So some of those, for example, we've got a smelter in Kazakhstan that uses both flat bed blending and bins on the same site for two different furnaces. So you can use either quite successfully. Same in Africa, we've got a smelter that uses bin blending and also flat beds there. My experience with MIM, they had the radial flat bed blending, which worked quite well. A little bit different to linear blending. So in the radial one, you keep stacking on the back of your original pile. One of the advantages of that is that you don't have to encounter heads and tails of previous piles or separate piles. We did try separating piles in MIM, so it can be done, but in between those piles you get this area of heads and tails of the pile that's a little bit different to the rest of the pile in terms of blend, so it can be difficult to move through that period. The bin blending, again, it can be done well. It's usually cheaper and easier to install and operate. The issue there really is that you get a lot of, if you get variation in the one feed, you will need to do a lot of pre-blending anyway to make sure that feed in bin one is the same all the time. And often with bin blending, the other issue is people make mistakes, put the wrong material in the wrong bin, and then you're forced to stop and empty bins and start again. I'll let Oscar talk briefly about his experience with feed blending.
Hello, well, I am Oscar Mendoza. I also come from a long time working in different smelters. I started in Chile, in Alto Norte, working around 10 years over there. In Chile, we got a smelter a little bit different than the other we got in Glencore because it is an Oranda reactor with a injection system. We inject around 90 or 95% of the con straight away to the back. And the blending system over there is more like bed, but like a linear bed, but we did a small, we do a small bed with a loader actually, which is, I believe, is one of the worst conditions when you are doing a bed with a big loader. It's a 100-ton bed, 60-ton bed to blend it and feed the smelter. But over there we have this bed combined with beans, and we have a couple of beans when we feed the other 10% of the bed of the concentrate, and another maybe 30 to 40% of rivers. and that gives you a lot of flexibility to change the recipe very quick. And the normal reactor have the advantage to have a very big bath when you have a long residence time, and you can do a quick change into the feed, and the furnace can manage and give you a good average. Yeah. After that, it was same as a BEM, a little bit of while working in Mount Isa mines. Mount Isa have this donut one, which is Ben already explained. But my overall comment is there is not better system than others. There are different systems. If you have a lot of variability as a custom smelter, have a massive bed is not a good idea, because you need to change when a mine change the profile or something happened in the road or in the train line. Sometimes you just have not come to blend and you have to move quick. The other way, the big bed like donut or the linear one give you a very consistent feed, which is also good. For me, will depend of what are your conditions. You are custom, you have a mine, you have consistent feed, you don't have consistent feed, which is better. But for me, the answer is it's a combination. You want to have flexibility, you need a big bed with a couple beans, and then you can swap and change and maximize your revenue. And also, I think that is one of the main questions we got from the masterclass. And in a way, we have a question related with the MPE and how MPE can help you. Maybe, Ben, you can start with the example we got in Africa.
Yeah. So we've rolled out MPE and feed blending to a few of our Glencore sites and a few of our ISASMELT licensees. We've used it for planning the feed, and often that's because sites have started receiving custom con and had to encounter something like what Stanko was showing earlier. So we've got a new feed. We don't know if we can treat it or not. We're not sure what effect it will have. We need to put it through MPE and see what it does.
We don't want to find it into the furnace.
That's right. So traditionally, if you can't find something wrong with it, you put it in and see what happens. But a much better approach is to test it with a package you can trust. So we've used this package with several sites, lots of different concentrates. So quite reliable, and same with the energy balance. So quite accurate. You can tune it to your plant, of course, with your own assays and your own results from the plant. The other place where we've really used MPE and a bit of feed blending is when we want to try something, a new configuration of the plant. So we want to skip a step. We want to make a different mat grade or a different type of slag. We can test that in MPE, and that gives the operators a good starting point, what specs they need to run.
Non-conventional feed, for example.
Exactly. Yeah.
Something with high carbon or graphite, you can identify in MPE what will happen in the energy balance and everything.
Yeah, that's right.
Also, what we used to use in our Australian smelter with the ISASMELT, it is to find the right ratios. I know a few smelters in the world with them using the silica to iron ratio fixed for 25 years, maybe more. And then with MPE, you can choose, as Stanko showed in the presentation in the Excel tool, you can choose a little change into the silica to iron ratio, and that will give you a better slag quality, and better slag quality have many advantages. But the main one, in my view, is keep your copper losses low and keep the business profitable with a good mass balance and good metal balance. And you don't have to wait until do the end of month metal balance to see if your slag change. You can know before, when you are planning, if your slag will change, because it's a question, for example, about the alumina. We got an example just this weekend. As we talk, we are not just a technology provider, we are an operators. Yeah, this weekend was a long weekend in Australia, and someone in our operations something happened. We have an issue in the furnace, And talking with the technical superintendent, we realized actually was a change in the alumina. The alumina went up a little bit, but consistently. And we realized, okay, what we have to do, what is the typical effect when you add more alumina? The answer is can be everything, depending on what else you have in the bath. In this case, we have an increment in the alumina content in the slag. And we said, okay, what else we have there? We also have a high calcium oxide content. Okay, what's up if we drop the calcium oxide? Or we have to increase the calcium oxide? Yeah, we jump into MPE review. Okay, what's up if I increase calcium oxide? No, wrong decision. You have to reduce the calcium oxide. Okay, reduce how much? 1 point less. And in a couple hours, we was able to change the recipe. Yeah, and improve the furnace performance in maybe 1 day, 20 hours. And that is the advantage also to have beans and the bed, because in Mount Isa, if we have, you only realize, you only trust in your donut. If you want to do a change, you have to wait whatever the amount of corn you got in inventory. But if you have a bean, when you can change, for example, your limestone addition or a special corn, the new corn you have, you can make a quick decision to reduce the rate of this bean to control the overall quality. Yeah. Other thing I want to highlight is we are not an MPE sellers. It's a question over there if we can do training. Yes, we can do training, but MPE is not our software. We don't sell MPE, but we can sell that. We can help you with the training. And for me, the most important stuff is, for many years, the people or the metallurgists as us, we are using the multi-phase diagrams, using a paper or using this big book we call Slag Atlas. And you have to choose the right graph, do the interpretation, and try to find the closer to your field. And today, with this tool, you can do your own calculation with your specific field, and that will give you your viscosity, solid percentage, and everything. It's not a full representation of the real life because there is estimation behind the software, like the database we have inside and everything, but give you a much better approximation of our old Slag Atlas. I still have my Spanish version. I have to review sometime, but that's the power of the tool. That's you saw in the Stanco Excel tool. What else we have?
We've got another question here. So how adaptable is the package with other smelting technologies? So we have used it within our group for flash smelting. Obviously, you're looking for different outcomes in terms of percent solids or viscosity or operating temperatures there, but you can do that. As Oscar said, the big advantage is you're really doing a multi-phase calculation, so you can take into account everything that's come in the feed and get a result that can be used on the plant to help run the plant before the feed arrives at the plant, I think is the main point.
Ideally.
We've got another question came up, which is about the feed blending and how important it is. So in particular for furnaces with a small bath like the ISASMELT, it's important to get that blend right. Very low residence time, so you'll see a change in feed come through very quickly into the bath. And I guess the other point there is that with many furnaces and smelters, you can relate the variation in the output almost directly to the variation in the input, which means you really need to put your focus on the feed blending rather than just trying to sample quicker and better and make quicker changes to the furnace. And as I said, more applicable for the furnaces with lower residence time or smaller baths. But yeah, that's what we've seen numerous times across many smelters.
Yeah. And also give you a good advantage in the business way. When we said the smelter business is trying to make money in incremental actions. And one of the good incremental action we have with these small batch technologies, is you have to take care of. You need to be careful to have focus in your blend to make sure you have a good bath every 15 or 20 minutes, whatever your bath recovery is. Yeah, and then that give you it's not a warranty, but you for sure will have a good copper recovery at the end because you are having a good slag at the start. Yeah. Another point to highlight is with our technology with a small bath, you also have a very good turnaround when you have to do a maintenance and you need to recover the bath because it's a small bath. We can recover a molten metal bath from zero in hours, let's say 8, 12, 16 hours. It's not a week or days activity as a flash smelter, for example. And also you can start the bath from slag, crush slag. In the Noranda reactor, we have to take care of all the molten metal sieve and put in a furnace and put blanket in to keep the molten metal hot during the maintenance. Yeah, which is doable, but when you realize how easy it is restart the bath or whatever in hours, it's something with added reliability and running time to your operation.
Good. All right. We've got one last question and then I'll hand back to Stanko. So the question was, we see that MPE relies heavily on mineralogy, but can we use it if we've only got elemental assays? And the answer is yes, you can still use MPE, it will still give you outputs. What won't work in that case is the energy balance or the energy output. So if you can calculate that or determine that another way, then you can just use assays from that.
And you always can manage your energy balance relating the bath temperature and managing the river consumption or the fuel addition, which is a whitometer and above.
Correct. All right, there is a lot more questions. We don't have time for them, but we'll hand back to Stanko and we'll endeavour to answer some more of those after the webinar. Thanks, Stanko.
Excellent. Thanks very much, Oscar and Ben. I think that you've really gone through a lot of the questions that have come in from the different participants. So no, that's really good. Thank you for taking the time with that. And really, when I consider what is the actual, you know, what we've been going through today and what's important, I mean, I think that really, I think we've struck a chord. There's over, I mean, close to 30 questions now that have come in. There's also a number of different, I guess there's a few people chimed in with their also support and advice on how the different systems come together. So I think, you know, thanks very much to those of you that have put in your thoughts there. What we're going to do is, with all of the questions that have come in and with this this information from various parts of the world and smelting space, so we're going to put that all together in a package and issue that to everyone. We will answer the questions to the people that have asked them individually, so you'll get that response quicker from us as a team, and then we'll be able to look at giving you that information so that you can really understand those sort of next steps for how you can use this type of package, how we can help you, but also how you can improve the operation of your own smelter. So I want to take a moment to thank everyone for attending and joining us today. It's really been good to have you part of this first masterclass. One of our poll questions is, where should we take it next? And we'll take your feedback from here and look at putting the order of our program to what we see as being requested by the world, and being able to then tune what we are presenting to you guys out there, and really to make sure that we address those key needs. So again, thank you very much from all of Glencore Technology, and also from myself personally and Oscar and Ben for your time today. If you want to reach out, if you have any other questions, please use the email address that I've got on the screen. Also, hit us up on LinkedIn and follow our page and have a look at all of the posts that we have there in the different areas. You'll be able to track us down there as well if you want to find out more details about what we do. So that would be great. As you can see, we are involved in technologies for minerals processing, obviously the hydromet space, which is another group that I look after, as well as in the copper refining space. So this is our ISASMELT technology. So please have a look at our websites, LinkedIn, and find out more about us and reach out. And we will be in touch in the coming weeks with the responses to your questions and within the coming months as to the whole package that we're putting together through all of the masterclasses. So thanks very much again, and we will close the evening. So all the best from us here at Glencore Technology.